I'm going to try and pull everything that the previous speakers have said about the disease together. So starting with, we have a mountain of data. So a few examples were given, like the lab trials of Stuart, the genetics trials of Natalie. This morning, we were introduced to a monitoring program that's being funded to go out throughout the country and actively look at diseases. And then we've got remote sensing data. So how do we pull that all together and use that for risk prediction and decision making? So the research goal of the part that I'm telling you about is really to build a single model that allows us to predict the likelihood of red needlecast at a given time and place. So everything that information that you may have available, like recent weather data. You may or may not know the genotype of the tree you have planted. You probably know how old your forest is. You may know the current state. Is it disease-free or mildly or heavily affected? You may have scraped copper in the past. All of those things you can, if you have a single model that does that all, you can pull that together and then figure out how likely am I to have a disease, and how is that going to develop in the future. So the way we did this particular research, and it's really only the last year and a half that we started pulling this all together, so we took all of these individual data sources and first modeled them separately, and then extracted one or a couple of key parameters and used that to put it into this integrated model. And then we automatically get the weather data for the whole country, and we know all of the geographic features as well. Like elevation, slope. Are you in a valley or on a hill? That all matters. And then, as a last step, we're putting a user-friendly interface on top of it, so that it's actually a practical tool that everybody can use, both other researchers and other groups, because we don't want them all to have to reinvent the same wheels that require programming, but also, for foresters that just want to manage their forest. So I don't expect you to read this diagram, but just to give you an example, each blue box, this is not even the whole thing, but each blue box is an individual trial or data source. And then each purple box is a different model. And then basically we kind of pull that all together into a single, the blue box at the bottom. So for example, everything that Natalie talked about for these elite clones, basically we take this one ranking. So all of the, if your genotype that you've planted is one of those, we can take that information along and see how sensitive it is. So I'll show you for each of the different types of information that we have, I'll show you just one example. So the first one is lab trials. Natalie did this pre-screening, and this is not the elite clones. This was something else called industry-relevant clones. So that's, I think, the majority of genotypes that are planted today. And there were about 45, and we took the 4 most resistant and 4 most susceptible, and a detached needle assay was done with that. So this is the end result of that whole study. And basically, what you see is, on the left plot, you see sporangia, which is actually the spores that come back, grow back out of a needle as a function of time. So you see that the ones out of the pre-screening, the susceptible genotypes were 3.5 times worse in terms of spores coming back out than the resistant ones. So that number 3.5 is then the only number we kind of take along and put it into our integrated model. So another one is this field observation. So I think this database that we're using here is the same that the field monitoring that was described this morning from the inspectors that go out to ports and basically go throughout the country, plus all of the disease reports that come into Scion's diagnostic lab. So by now that's 10 years worth of reports, so 40,000 individual reports, out of which I think about 400 were positive for red needle cast. So that comes in. We show it on the picture on the, I don't know, again, point, but on the left. So those are all the observations that were made. Lots of different diseases. So you see this big concentration on the central North Island, not strange. But you can also look at this over time because it's 10 years, and you can really see the disease spreading from the central North Island, and going south over time. Then we correlate that with geographical features. So I showed only two here, elevation and slope, but we have others that basically, capture like really the local environment. Like, are you in a valley or on a steep slope, or are you just on flat land? And then all of the weather data. So on the right you see 10 years worth of, in this case, precipitation, where we know for every day how much it rained. And then we can correlate that with the positive observations of red needle cast. And we put all of that together in a single machine learning model. And that allows us to draw conclusions about what geographical features are most important for the occurrence of red needle cast. And this one is the one genetics trial. So we know exactly, right here they're just labeled G0 to G43, but we know exactly what genotypes they are. So they're labels of the RPBC. And basically that allows us to give a numerical value to, given this genotype, how susceptible is it? And so, the average is 1. So if you don't know your genotype, in our model we just take an average of 1. If you do know, we can put that in. And typically it's anything between 0.5 and 4. So there's pretty large variation. And then we have our big integrated model. It's not completed yet, but we have enough that we could build a first useful tool on top of it. So this is a copper spraying decision support tool. So the idea is, it's a simple web interface, and this is a screenshot of it. You can pick a date, you can pick a genotype, you can pick a location from a map, or just entering in your coordinates. You just go to Google Maps and figure out where your forest is. You put that in, and then you can run the model, and it will predict forward 1 year in time. And it just gives you on the vertical axis the probability that red needle cast is actually going to happen. And I'm showing this now. There's still a year worth of work to do in this program. So a lot of this is not yet final and validated. And we have to integrate a lot more data sources. But we are now at the point that it is practical, and we've kind of designed it in a way that we think is useful for US forest growers. So I don't have time to demo this tool now, but I'll be around in the tea break and after the next session. So I have it actually with me running on my computer. So if you want to play with it, we're actively looking for feedback. So it would be really interesting to just come and talk to me. So what's next? So we are now trying to get feedback. Today is one of those times. Basically, by the end of this year, we will, kind of deploy the first version of this tool internally and see, if it actually, is useful to other researchers. And then throughout 2019, when we have integrated more data, we will do a few targeted beta tests. And after that, we should have something that we should make available to industry. And we're right now figuring out what the best way to do that is. A web interface, or integrate it with a tool that you already have. So ideas about that, if you have those, also very interesting to hear. And then, the rest of the year, we will integrate more trials. We'll integrate a growth model. Then Stuart showed this cost-benefit analysis, like the economics of it. We haven't integrated any of that yet. And then, figuring out the productivity disease impacts as far as we have the numbers for. That's all I had. Thank you.